This is a lecture for your benefit about Newman projections. Welcome. And this will follow from a packet which has been registered from the following slides. So these slides here have turned into a packet. For 9 Newman projections. So I've assembled the relevant slides and turn them into a packet which has this first page on it. But before we would move into the packet, I'd just like to present some brief motivation and background and context for this topic called Newman Projections, found in Chapter 4 of your textbook. As you are aware from Chapter 1, single sigma bonds rotate. Right now, both green atoms are up. I can leave this atom arrested and immobilized and turn the other atom freely. And now I'm allowed to have, this is a different, what you're looking at is a different conformation or shape, a different shape of the molecule. There's this shape, there's that shape. I can rotate this any number of 360 degrees, 22 degrees, 84 degrees, and each of these degrees of rotation would give a different shape because sigma bonds are flexible. They can be rotated, and certain shapes will be more stable than other shapes. For instance, this is the eclipsed shape. That's not as stable as the anti-shape, where one green atom is up, the other green atom is down. So certain shapes are more stable than other shapes. There's also the gauche shape, which is a little offset. Gauche, G-A-U-C-H-E, a little offset. And finally, there is the partly eclipsed shape. You're looking down the carbon-carbon bond, and I'm having trouble seeing this bond right now. It's eclipsed by what? By the bond in the front. So certain shapes are more stable than other shapes. Sigma bonds, what's more important at this point is sigma single sigma bonds can, yes, they can be rotated freely without losing orbital overlap. That is not the case for double bonds. See, please note that's a double bond. And because if this was rotated, orbital overlap would be destroyed. So we have one atom, one white atom up, one white atom down across the double bond. This is the down, this is the up. And I try as I might, I cannot rotate this. It snaps back. This is remaining as this shape. So double bonds do not permit rotation. Single bonds do. So we're looking at species which have single bonds. Because these single bonds can rotate, it allows for different shapes, and different shapes have different stabilities. A shape in organic chemistry is called a conformation, a different conformation. This is a different conformation or shape. That's a different conformation or shape of this very same molecule. Different shapes or conformations of the molecule, because I'm allowed to rotate the single bond, and in rotating it, it's not broken. So let's turn about with that introduction. I hope that went well, and we'll turn into the packet materials. As you see, I have some notes already prepared. So let's consider an experiment where a molecule, such as I have here, has been enlarged so that it's 6 feet tall, the same size, same height as a human. A molecule has been enlarged, and a stick person stands, as you see, to the left of it. And the stick person has a laser pointer, and they can shine a laser pointer in between the wedge bond, which is more toward the front, and the hash bond, which is more toward the back. Please note when you're looking at this that the wedge, you can see the black color of the wedge in front of the blue laser, and the blue laser in front of the hash. So take note of that, please. That layering, wedge in front, then laser, then hash. And there were some questions here. And if you wanted to, you can hit pause. I'm not going to, but I could take off my glasses and put my face flush to the screen and kind of get that idea of what we're going to do with respect to gauging if something is more to the right or more to the left of a point of view. So from the stick person's point of view, the stick person is standing to the left from their point of view. Is the deuterium atom, the D, is that more to the left or more to the right? So if I take my glasses off and I put my face flush to the side of the screen from that point of view, because a wedge projects as it does, what do you think this answer is going to be? I will let you know that it's going to be to the right. The deuterium atom is to the right. The methyl group, also on the far wedge, here's the methyl here, is also to the right-hand side. From that person's point of view, looking this way, the deuterium atom and the methyl atom are to the right. The ethyl group, let's record that as more toward the bottom, isn't it? More toward the person's feet. And in choosing between the ethyl group and the hydroxyl group, OH, which group will be more distant, more away from you? That will be the hydroxyl group. That will be more distant, further away from the person's face. You can measure it in centimeters if you like, or inches. So we'll just take the word for it. So those are our recordings there. And likewise, if you're looking for the rest of the pieces up above, the hydrogen and the chlorine will be to the left. To the stick person's point of view, comma, the hydrogen and the chlorine are to the left. Now let's look below. We're now looking at the bottom partition of this handout, below the rectangle. Thank you for following along. This experiment, again, a molecule has been enlarged, and this time the stick person has perambulated to the right, has walked to the right of this blown up molecule. And again, they got this blue laser, and they're shining the blue laser in between the wedge and the hash. Just goes to show you that the wedge is more toward the front. That's why it appears thicker and bigger, because it's closer to you. The wedge is nearer to you from the seat on your chair where you're sitting right now. The wedge is closer to your face than the hash. That's why the hash appears kind of fuzzy. This bond appears kind of dashed because it's further away from it. It's kind of foggy. So that's, again, we talked about this in chapter 1. So I hope you're bringing this information along with you. And please note again, when you look at the layering that I see here, that this wedge is more in the front. It blocks our view of that blue line, that blue laser, because it's in the front. It's blocking our view. And there you have the laser. And the laser blocks our view of the hash. So it's layered. Wedge, laser, hash. For closest wedge, laser, furthest away, hash. And so now if I take my glasses off here, which I don't always do, and I put my face to the left-hand side, to the right-hand side where this person is, I put my face there, then these answers maybe become more approachable. So once again, to restate that, because I messed that up, if I take my glasses off and put my face right where that person is located, now, based on what we talked about with this layering, how does it look to you? Is the methyl group to the left or to the right? This time, the methyl group is to, I hope you got it right, the left is to the left. I hope you got that correct. And this time, the deuterium atom is also to the left. And the ethyl group will be more towards, again, the bottom. And just for the record, to the stick person's point of view, the hydrogen and the chlorine are to the, this time, the right. Forgive me for doing this again. Take my glasses off, put my face where the stick person is, understanding that a wedge projects as it does and the hash projects as it does with the laser in between. The hydrogen and chlorine are to the right. So this is progress towards making Newman projections. Next leaf, or one of the leaves in the handout, tries to reconcile what we just talked about. Is it to the left or to the right? Is it to the bottom or the top? Brings a line angle formula through a sawhorse projection, which is the intermediate bring along track changes courtesy diagram, and to what we want the Newman projection. So I have we want to look kind of I know there's a lot on here, so you'll want to try to look kind of right here. Okay, that's where we're starting, right about there. Okay, and we want to construct a table recording our observations. Okay, so the stick person stands to the left. Let's record, is the CH3 group up or down? Isn't it up? Doesn't it have more altitude? It's at eye level. It's not at foot level. It's at eye level. So the CH3 group is up. And because the CH3 group is on an in-plane bond, not on a wedge, not on a hash, it's neither left nor right. It's straight up, neither. Now have a look at the deuterium atom. The deuterium atom, that's below the person's waist, isn't it? It's more down. Let's record that. It doesn't have such an altitude, does it? So now I will remove this box. And based on what we talked about before, if I took my glasses off, understanding the layering, wedge, laser, hash, if I took my glasses off and put my face like that, I will record for you that the deuterium atom is to the left. Again, the fluorine, isn't the fluorine at the same level as the person's shoes, not at their head? So we'll put that more down toward the floor. And this time that's to the right. And the chlorine atom, find it right there. It's more up, it's at eye level. It's neither left nor right because it's not on a wedge or a hash. Find the hydrogen. And I think you already solved this, didn't you? Because the person's still standing in the same place, right? They're still to the left. Okay, so you can use your answers from before here. They're just as legitimate. Look at what the deuterium was. The deuterium was on a hash. The hydrogen's on a hash. They're going to have the same answer. So the deuterium was more down, easy to tell, and your answer should be internally consistent. Bromine, you can use your answer from fluorine to figure this out. More down, of course. And it's some more to the right. Time out for now. When you see a sawhorse projection, it starts like this. That's what we started with. We were given this here. Pardon me. We were given this. Now, if you put it, bank it like that, that's sawhorse. And if you put it straight on, that's a Newman projection to you. Okay. So this is, you're given a line angle formula, bank it. You're looking at sawhorse. And now this is full Newman projection, straight on to you. And with our table, you're seeing this borne out. And the Newman projection. Didn't we record that deuterium was down and to the left? Here's deuterium. It's down. This is a Newman projection. On the whole, it is down and to the left. Talking about deuterium. On the whole, it's down and to the left. Deuterium is. We plotted this already, checking our, this is the Newman projection that comes out of it. We're just checking our points of view here. Looking at the CH3, we said that the CH3 from this point of view was up and neither to the left or to the right. There you go. And the fluorine was down and to the right. Was typed. Here it is in real life on the Newman projection. And you'll find that the atom closest to you is given on a type of carbon atom called, drum roll, a spoke carbon. Not a junction, not a vertex, not an endpoint, but a spoke carbon atom. And the spoke can be in the shape of a Y or an inverted Y. There's two kind of chances for a spoke. And because when on our recordings back here, we had up, down, down, we're going to choose this spoke, up, down, down. We're going with this one as the accurate spoke for this case. Up, U, down, D, down, D. The spoke carbon is nearest to the stick person. point of view. Not to be forgotten, the carbon atom furthest away from the stick person's head, more distant from the stick person's head, is called the sphere carbon. These aren't words I came up with. These are textbook terms. The sphere carbon, not the junction, not the endpoint or vertex carbon. This is called the sphere carbon. More distant to the stick person point of view. These are sphere carbons over here. Let the record show. Sphere carbon. Sphere carbon. And if you look back at our records here for chlorine, bromine, and hydrogen, chlorine, hydrogen, or bromine, it was up, down, down. And which sphere would capture that information? This one here. And class, it turns out that from this molecule, we having the eclipsed conformation or shape from this information. This it's like a child at a playground. You know, one time the child is going down the slide, next time the child is on the seesaw, next time that the child is doing pull-ups. So it's you can take a picture of a child at a playground and then they're on to the next thing. So this is in the case of this molecule. This molecule is not a rock so long as the absolute temperature is not 0 degrees Kelvin. The molecule can jitter, move, vibrate. So long as it's not 0 degrees Kelvin, there is molecular motion. So this is just a snapshot of the molecule. And this snapshot, in this snapshot, the molecule has this shape. In this snapshot, the molecule has this shape. And as I said, certain shapes are more stable than other shapes. So let's take a new look at a new problem. I'll jump down to E and F. Okay, so follow me along I went to the end of the handout, E and F. I may assign these for, work outside class, but we're going to E and F. And now we have a chance to construct a Newman projection in its own right. So let's maybe try our hand at that. You would need to know which one is T-butyl. Just to help you here, this is ethyl here. This is N-propyl. Kind of gain your bearings, okay? Gain your bearings. This is what you're kind of breathing in and taking in, this information here, and we're going to plot it. And from this plot, we can turn it into a Newman projection. I'm now drawing two possible spokes. I don't know which one we're going to use. Your guess is good. You got a 50-50 chance as to which one is correct. You got a 50-50 chance. So there's one of two spokes, like the shape of the letter Y, and here are one of two spheres that we'll use. And now I'm drawing two up and one down. So we'll use one of these spokes. We'll use one of these spheres. Let's get going. So this is where he or she is standing, okay, right here. And so take a look at T-butyl. Is it up or down? I think it's above the person's head, isn't it? I mean, they have to crane their neck up. So let's record up. And it's neither left or right. It's on an end plane bond, so it's neither. It would be straight up. straight up erect. Here's Ethel. Okay, I can do this again. Turn off the glasses, put my face close to the screen. Remember that layering, wedge, laser, hash? Remember that? So let's record here that Ethel is down, more down than T-Beetle. T-Beetle is up, Ethel is more down. And because of that layering, it's gonna be on the right. Ethel's on the right. Hydrogen will be on the left with respect to this person's point of view, down and to the left. We got 1 up and 2 downs. 1 up and 2 down. Which spoke best fits this descriptor? You got it. It's this one. I can feel free to use T-Beetle here, T-Boo. That's good for you, good for me. And just complete your table here. Ethel is down and to the right, so plant Ethel here. Whoops, I should be doing this for the sphere, excuse me. This is the more distant. So, and let me go back here and here we have the sphere, because it's this carbon, that vertex is more distant to the person's point of view, and the other one I will try to draw here. This is the spoke carbon. Should have been doing that for the sphere, and I barely caught myself. Thankfully I did. 1 up and 2 down. Well, it looks like this is the correct entry to use, and now I'll get going in a correct fashion. So following up with this information, slotting it below, T-Beetle is up. And Ethel is down and to the right. Partial credit is afforded. And hydrogen is down and to the left. Okay, we have one part of the Newman projection. Now let's take a look at the hydrogen, the N-propyl, and the amino, or the NH2. So let's record that the amino is down. And it's neither on a wedge nor a hash, is it? The NH2. So it's kind of straight down. Here's the N-propyl. You can use your answer from before with respect to the hydrogen wedge. It's going to, this time the N-propyl isn't it the N-propyl above the person's head? So the N-propyl is up. N-propyl, let that be up. And this time it's to the left, like you saw for the wedge, for the hydrogen, to the left. And here's the hydrogen that we're concerned with. This one here, my cursor's flashing over it right now, that hydrogen, that's up. And this is to the right with respect to that person's point of view. So we have down, up, up. Can you pick the right spoke for that? Down, up, up. Which one is the right spoke? This one here, right? There's up, hand. See where the hand is? See where the hand is? Up, up, down. That's what we will like to use. We will put in this information here, NH2 on the down, and N-propyl up on the left, NPR, and hydrogen up on the right. So if you were to superimpose these, slide one over the other, then you have the Newman projection. So if I was to superimpose those, I'm now drawing the Newman projection. The answer is already handled. I just have to assemble it. Take stock of this, copy, paste, and propyl. what we're drawing is a certain shape of this molecule, frozen at any instant in time by a picture. Now, please copy paste what you see here. Hydrogen ethyl. And that is what this stick person is seeing by looking down the molecule's axis, by looking down its axis along the train of sight from the pencil here. Looking down the molecule's axis, that's what the stick person's point of view is presenting to their eyes. So if you would care to join me, this is a nice handout here where let's do example problem number 1. And that would end this segment of the Newman projection. So this is a nice handout because it presents to you which spoke to use and which sphere to use.